Introduction. Friends, we meet here to discuss the two important concepts of calculus, and these are continuity and differentiability. These two concepts rely on the concept of limit, and so first we make an attempt to understand the concept of limit of a real valued function. Definition: limit of a real valued function. Let f of t be a real valued function which is defined on some open interval I containing a point x. We say that f of t has limit L as t tends to x, or f of t has limit L at t equal to x, and write limit of f t equal to L as t goes to x if for every epsilon greater than 0 there exists delta greater than 0 such that mod f t minus L is less than epsilon whenever t belongs to I, and mod t minus x is greater than 0 and less than delta. Before we proceed, it is important to gather some important points related to the definition of limit. 1. We may write limit of f t as t goes to x is equal to L in the form f t goes to L as t goes to x. 2. Although in the definition of limit of a function at a point x we have assumed that the function f of t be defined on an interval containing the point x, it is not absolutely necessary to assume that f t is defined at the point x. The inequality mod t minus x greater than 0 and less than delta in the definition of limit clearly suggests that while evaluating the limit of f t at the point x, the value of the function f t at t equal to x has no role to play. 3. Limit of a function may or may not exist at a given point. If for a given function f of t its limit exists at t equal to x, then it is unique. Now, let us try to understand the concept of limit geometrically. Consider the function s equal to f of t, for which we have limit of f t as t goes to x equal to L. Geometrically, this means that for any arbitrarily thin horizontal strip h containing the line s equal to L, we should be able to find an interval I containing the point x such that the graph of s equal to f of t for t belongs to I minus singleton x lies completely in the horizontal strip h. We now consider some illustrations about evaluating the limit of a function at a given point. Example: evaluate limit of t square as t goes to 2. Solution: here, as the values of t get closer and closer to 2, the function t square gets closer and closer to the value 4. Thus, we believe that the required limit is 4. To prove this, we consider an arbitrarily small epsilon greater than 0 and determine a delta greater than 0 such that mod t square minus 4 is less than epsilon whenever mod t minus 2 is greater than 0 and less than delta. Choosing delta is equal to epsilon by 5, which should be less than 1, we see that mod t square minus 4 is equal to mod t minus 2 into mod t plus 2, which is less than epsilon over 5 times mod t plus 2, which is less than epsilon whenever mod t minus 2 is greater than 0 and less than delta, which is epsilon by 5. Thus, limit of t square as t goes to 2 is 4. In general, it can be shown that limit of t square is equal to c square as t goes to c for every real number c. This may tempt us to believe that limit of a function f t at t equal to c can be derived by inserting t equal to c in f of t. But this is not always true as seen in the following example. Example: evaluate limit of t square plus t minus 2 over t minus 1 as t goes to 1. Solution: here notice that the limit cannot be obtained by inserting t equal to 1 in the given function, because it gives us an undefined quantity. For evaluating the limit in this case, first we observe that limit of t square plus t minus 2 over t minus 1 as t goes to 1 is equal to limit of t minus 1 into t plus 2 over t minus 1, which is equal to limit of t plus 2 as t tends to 1. It may now be verified that the required limit is 3. Next, we consider an example where the limit does not exist. Example: for the function f of t equal to minus 1 when t is less than 0 and 1 when t is greater than equal to 0, show that its limit does not exist at t equal to 0. Solution: if possible, suppose limit of f t as t goes to 0 is L, then minimum of modulus value of 1 minus L comma modulus value of 1 plus L is greater than 0. Now, if limit of f t is L, then for epsilon equal to half of minimum of modulus value of 1 minus L comma modulus value of 1 plus L, there exists delta greater than 0 such that mod f t minus L is less than epsilon whenever mod t is greater than 0 and less than delta. But mod f t minus L is either mod 1 minus L or mod 1 plus L, and both these values are at least 2 epsilon. So, we arrive at a contradiction. Sometimes when the domain of a function is an interval of the type a comma b, we cannot talk about the limit of this function at the endpoints of this interval. However, we may investigate about the one-sided limits at these endpoints, which is sometimes useful in understanding the behavior of the function at the endpoints. The concept of one-sided limits. Let f of t be a function defined on an interval just to the right of x. We say that f t has L as a limit from right or right limit L at t equal to x, and right limit of f t as t goes to x plus equal to L if for every epsilon greater than 0 there exists delta greater than 0 such that mod f t minus L is less than epsilon whenever t is greater than x and less than x plus delta. Similarly, if f t is defined on an interval just to the left of x, then we say that f t has left limit L at t equal to x and right limit of f t as t goes to x minus is equal to L if for every epsilon greater than 0 there exists delta greater than 0 such that mod f t minus L is less than epsilon whenever t is greater than x minus delta and less than x. We saw that the function f of t equal to minus 1 when t is less than 0 equal to 1 when t is greater than equal to 0 does not have limit at t equal to 0, but it can be easily verified that limit of f t as t goes to 0 plus is 1 and limit of f t as t goes to 0 minus is minus 1. Basic properties of limits. Suppose limit of f t as t goes to x is L1 and limit of gt as t goes to x is L2. Then 1 limit of ft plus or minus gt as t goes to x is L1 plus minus L2. 2 limit of ft into gt as t goes to x is equal to L1 into L2. 3 limit of ft over gt as t goes to x is L1 over L2 provided that L2 is not 0. Note that the first two properties also hold if we have any finite number of functions instead of 2. These properties are very useful in the evaluation of limits of certain functions and sometimes in proving general results like the following theorem. Theorem: if p of t is a polynomial function, then limit of p of t as t goes to a is equal to p of a for every real number a. Further, for any rational function p of t over q of t, if q of a is not 0, then limit of p of t over q of t as t goes to a is equal to p of a over q of a. We saw that for polynomial functions and rational functions, the limit at a given point of their domain is simply the value of the respective function at that point. There are many more functions for which this holds, and this leads us to the definition of continuous functions. Definition: continuity of a function at a point. Let f of t be a real valued function defined on some subset d of R. We say that f of t is continuous at the point x belongs to D if the domain set D contains an open interval containing the point x, and further limit of f t as t goes to x is equal to f of x. If f of t is continuous at each and every point of the domain set D, then we say that f is continuous on D. If a function f t fails to be continuous at a point x, then we say that f t is discontinuous at x. From the definition of continuity of a function at a point, we infer that for a function f to be continuous at x, three things should happen. 1. The function f should be defined at x. 2. The function f should have limit at x. And 3. The limit of the function f at x should be equal to the value of the function f at x. Since these three things happen for polynomial functions everywhere, all polynomial functions are examples of continuous functions on R. The concept of right and left continuity. A function f t is continuous at t equal to x from right or left if limit of f t as t goes to x plus is f x, or limit of f t as t goes to x minus is equal to f x respectively. Remark: obviously, f is continuous at x if and only if it is continuous from right as well as left. Example: prove that f of t equal to mod t is continuous on R. Solution: let x be an arbitrary real number. In order to show that function mod t is continuous at x, we need to show that limit of mod t as t goes to x is mod x. Let epsilon greater than 0 be given. Choosing delta equal to epsilon, we see that modulus value of mod t minus mod x is less than epsilon whenever mod t minus x is less than delta. Because of the well known inequality, modulus value of mod t minus mod x is less than equal to modulus value of t minus x. Sometimes it is easy to judge the continuity of a function using its graph. If we can draw the graph of a function f in an open interval without lifting the pen, then such a function is continuous at each and every point of this interval. For instance, if we think about the graph of mod t, then we see that its graph can be drawn easily in any interval without lifting the pen. However, graphs are not always useful to decide the continuity of a function, especially when the function oscillates a lot. We take two illustrations to understand this. First illustration, let f x be equal to sine 1 over x when x is not 0 and 0 when x is 0. If we look at this graph of this function, then we realize that as x approaches the origin, the oscillations of sine 1 over x gets faster and faster. As a result, the function sine 1 over x takes every single value between -1 and +1 in the interval minus delta to delta, no matter how small is the delta. Hence, this function fails to be continuous at the origin. Second illustration, let f x be equal to x when x is rational and f x be equal to 0 when x is irrational. Note that this function oscillates so fast that it is difficult to plot its graph even in a tiniest interval. For investigating continuity of such functions, we cannot rely on their graphs, but have to follow the definition. Using the definition of continuity, here it is not difficult to establish that given function is continuous only at the origin. We now record some important results regarding continuous functions. Theorem: if functions f and g are continuous at x, then f plus g, f minus g and f into g are continuous at x. Further, if g x is not 0, then the quotient function f over g is continuous at x. It may be deduced from this theorem that a rational function p of t over q of t is continuous everywhere except the points which are zeros or roots of the polynomial q of t. Having established that polynomial and rational functions are continuous, we finally record a result about the continuity of exponential and logarithmic functions. Theorem 1. If b is any positive number, then the exponential function b raised to t is continuous on R. 2. If b is any positive number different from 1, then the logarithmic function log t to the base b is continuous on 0, infinity. The concept of derivative. Derivative is one of the most important tools in calculus. Its applications are not just in the field of mathematics or science, but far beyond, because it is associated with the study of change in one variable with respect to the other. The idea of derivative comes from the problem of determining the slope of a curve at a given point on the curve and determining the instantaneous rate of change of a variable y with respect to another variable t when the variable y is a function of t. We now give the formal definition of derivative. Definition: derivative. Let f of t be a real valued function defined on some subset d of R. We say that f of t is differentiable at the point c belongs to D if the domain set D contains an open interval containing the point c and the limit f of c plus h minus f of c over h as h goes to 0 exists. We call this limit the derivative of f at the point c, and we denote it by the symbol f dash c. The process of finding the derivative is called differentiation. Some of the other common notations for the derivative f dash c of f t at c are if f of t is differentiable at each and every point of the domain set D, then we say that f is differentiable on D and f dash t represents a function on D. Note that the concept of one-sided limits can be used to define right and left derivatives also. In economics, the concept of derivative can be used to derive the marginal revenue function from a demand function or a total revenue function, because it is defined as the rate of change in the total revenue due to an arbitrarily small change in the quantity of units sold. The simplest example of a differentiable function is constant function, whose derivative is 0 everywhere, and the identity function whose derivative is equal to 1 everywhere. We now take one example to illustrate the method of computing the derivative by its definition. Example: show that the function f x equal to x square is differentiable on R and f dash x is equal to 2x. Solution: here f dash x is equal to limit of x plus h whole square minus x square upon h as h goes to 0, which is equal to limit of x square plus 2xh plus h square minus x square upon h as h goes to 0, which is again equal to limit of 2x plus h as h goes to 0, which is equal to 2x. We have shown here that the derivative of x square is 2x. Geometrically, it means that the slope of the tangent to the curve f x equal to x square any point x equal to c is 2c. In particular, at origin this slope is 0 and hence the tangent to f x equal to x square at x equal to 0 is the x axis, as can be seen in the picture. Differentiability is stronger than continuity. It is a very simple task to show that if a function f t is differentiable at a point x, then it is also continuous at x. But the converse of this does not hold in general. For instance, we have seen that the function mod t is continuous everywhere, but this function is not differentiable at t equal to 0, because the limit of the quotient mod h upon h as h goes to 0 does not exist. Rules of differentiation. Let us now consider some rules of differentiation which are helpful in evaluating the derivatives. Constant rule: if f of t is equal to c for all t, then f dash t is 0 for all t. Scalar multiplication rule: if f of t is differentiable at t equal to c and alpha is a real number, then the function alpha f of t is differentiable at t equal to c and alpha f dash c is equal to alpha into f dash c. Sum, difference, product and quotient rule for differentiation. If the functions f of t and g of t are differentiable at t equal to c, then the functions f plus g, f minus g and f of g are differentiable at c, and f plus or minus g dash at c is equal to f dash at c plus or minus g dash at c, whereas f g dash c is equal to f dash c into g of c plus f of c into g dash c. Further, if g c is not equal to 0, then the quotient function f over g is differentiable at c and f of g dash at c is equal to g of c into f dash c minus f of c into g dash c divided by g c whole square. Power rule for differentiation. Let f of t is equal to t raised to p, where p is any positive real number. If p is greater than 0, then f is differentiable for all t and f dash t is equal to p into t raised to p minus 1. If p is less than 0, then f is defined for all non-zero t and f dash t is equal to p t raised to p minus 1 for all t not equal to 0. The power and some other rules of differentiation discussed so far can be used collectively to prove that polynomial and the rational functions are differentiable wherever they are defined, and further the derivatives can be easily computed using these rules. Derivatives of exponential functions. If b is any positive number, then the exponential function b raised to t is differentiable for all t and d by dt of b raised to t is equal to b raised to t into log b to the base e. In particular, d by dt of e raised to t is equal to e raised to t, that is, derivative of the function e raised to t is the function itself. Chain rule for differentiation. For functions f and g, suppose g composition f is a well defined composition function on the domain of f. If f is differentiable at c and g is differentiable at f of c, then the composite function g composition f is differentiable at c and g composition f dash c is equal to g dash of f of c multiplied to f dash of c. The chain rule is very useful to simplify the calculations on numerous occasions. For instance, if we have to find the derivative of fifth power of t square plus 1, then we can find this by expanding it and differentiating the expansion term by term. But this will be a very time consuming process. On the other hand, if we define f of t is equal to t square plus 1 and g of t is equal to t raised to 5, then g composition f of t is fifth power of t square plus 1, and by the chain rule g composition f dash t is equal to g dash of f of t multiplied to f dash of t, which is equal to 5 times fourth power of t square plus 1 multiplied to 2t, and this is equal to 10t multiplied to fourth power of t square plus 1. Inverse function derivative rule. Let s equal to f of t be an invertible function defined on an open interval containing the point t equal to t naught and s naught equal to f of t naught. If f is differentiable at t naught equal to f inverse of s naught, and if df by dt at t equal to t naught is non-zero, then f inverse s is differentiable at s naught and df inverse over ds at the point s equal to s naught is equal to 1 over df by dt at t equal to t naught. Since log t to the base e is the inverse function of e raised to t and d by dt of e raised to t is e raised to t, using the inverse function derivative rule, it may be verified that d by dt of log t to the base e is equal to 1 over t. Summary. We discussed the concept of limit in detail and see how it leads to the definition of continuity and continuous functions. We learn certain examples of continuous and discontinuous functions and get familiarized with certain properties of continuous functions. The final part is dedicated to the detailed introduction of derivatives, which are very useful objects in the field of science as well as economics. We learn certain examples of differentiable functions and discuss some of the rules of differentiation. These rules are very useful while investigating the differentiability or while computing the derivatives of certain functions. Thank you.